Hello, this is the video for the presentation I held last week in Hatfield. It's called an extension of procrustes analysis to aggregate idiographic attribute datasets. And I will more or less repeat the same talk I've given there, so you may watch it. So what is this talk about? I will skip the abstract. What I'm going to talk about is about single grids and later on about multiple grids. So single grids, just to get started, everybody has to know what is a repertory grid and what is a biplot. And then we look at so-called shared semantic spaces that are generated using procrustes analysis. And my work, which extends this shared semantic space on so-called joint procrustes analysis. So let's start with the repertory grids and biplots. These are the formulas we're going to talk about, but actually not. This is a formula-free talk, but behind everything we see here is linear algebra. So the formulas you see in the background, but this talk is purely conceptual. If you are interested in the mathematical background, you can refer to my PhD thesis, which has not yet been published. Repertory grids and biplots. So this is repertory grid data, and I assume that you're more or less familiar with it. This is the famous Booker grid from a schizophrenic patient. And we see the elements up here. We see the constructs, the left construct pole and the other construct pole here. And we see Irene has a value of 6 on this construct, so 6 refers to the right pole. In this case, Irene is described by getting along with conflicts, while the self is balanced, so the opposite pole, the left pole applies. That's the way we read a repertory grid. But now let's have a look at the 6 here, and keep in mind that Irene has a value of 6 on this construct. Actually, we see nothing from the data, or not a lot, let's say. It's not ordered, we don't see any systematic patterns, or at least I do not see it. And this is difficult usually to spot patterns with numbers. We need some other kind of visualization to be able to see that. And one way to visualize repertory grid data is a biplot. A biplot is a multidimensional scatter plot. So the simplest form of a biplot is a biplot with 2 axes, and this is what we usually call a scatter plot. And a scatter plot works in a way we all know. We have, in this case, 2 axes, x and y, and we have a point in this 2-dimensional space, and we read off the values on each axis by projecting the point in the space onto the axis. So this projection gives us the value on the x-axis. The orthogonal projection on the other axis gives us the value on the y-axis. This is the principle that's exactly the same if we add more dimensions. So let's have a look at a biplot with 5 dimensions. We have variable 1, variable 2, and so on. But the same principle applies. There's no change in principle here. We have a point in this multidimensional space, and we project. In this case, we only see 2 dimensions of it, but behind it is a multidimensional space. And we project again the point in the space on the axis orthogonally, so here's a right angle, and we read off the value. On the first axis, we do the same to the second axis, to the third axis. Oh no, where's the third axis? This one, and so on. So this is more or less the same. Let's look at the Booker data then. The Booker data, here I added the first constructs, and don't get confused because I accidentally swapped the poles. So get along with conflicts should be on this side and balanced over here. Sorry for that. But let's remember, Irene had a value of 6. The values are still correct, and if we project the element Irene on the axis, we see it fairly well reproduces the value of 6 Irene had on this construct. Now we can go ahead and add more axes. So we have a full biplot now with all the constructs, or axes if you want to call it axes, from our repertoire grid dataset. You will see Irene is quite peaceful, Irene is balanced and has wanderlust. Actually she's not, because the poles are swapped in this plot, but this would be the way we interpret it. She's rather scientific, open-minded, socially minded, has high values when we project on these axes. If we project on these axes, discursive, she's somewhere in the middle. She does not have that high values there. So these discursive does not apply, but she's somewhere in the middle. She is rather dreamy, playful, but not to the extent she's peaceful, wanderlust, and balanced. But the ideal self is different with respect to some of these attributes or variables or constructs. So that's the way we read a biplot, and we see ideal self and father are pretty close to another, and we might infer some ideas or hypotheses from this. So now what can we do? We've seen what we can do with a single plot. We can create a biplot, for example, to visualize the data. We can do the same actually with many biplots or with many grid data sets. And the way to do this is to use procrustes analysis, or generalized procrustes analysis, which is abbreviated GPA, and we will see that abbreviation quite a lot. So if you see GPA, it's generalized procrustes analysis, and we can use it fairly well with grid data. So this already is a result of what we will see and we'll see in a second how that works. And this is a biplot on a higher level, we might say, and I call it a shared semantic space. And what we see here is basically a superposition of many biplots. So many biplots, each biplot generated by a grid data set. And it turns out that when we apply the GPA method to, and we will see later on how that actually works, but if we do that, it turns out that if we're lucky, we get a shared semantic space. That is, we have the elements in this space, and we have again the axis around. So appreciation is over here, indifference over here, and it's kind of an axis. But in this case, this is not one single person, but it's the average of 40 persons. So 40 elements, in this case the company today, and the average lies here. Then we also have incompetent company and company's potential. And here the same logic applies, the biplot logic. So let's look at this. Here we have an axis. We have uncoordinated work by individuals, the one pole. The axis runs through the center, and synergetic teamwork on this side. And now the same applies. We project onto the axis and see the company's potential is synergetic teamwork to have that kind of teamwork. The company today does not quite have such synergetic teamwork as their potential is. And an incompetent company is more related with uncoordinated work by individuals. We can do the same with the other axes, from introverted, slow, to clear and flexible, and so on. But the good thing about this shared semantic space, and that's basically why it's called a shared semantic space, is that this space not only applies to one individual or to the average, but to all individuals. Let's see what this means. In this plot, we see 3 points, or we see many lines, which start here at the company today element, which is the average of all 40. And here we see the single ones. So for each line, or the end of each line, represents an element from the grid of a single interview. So here we have company today, the element company today, the position of the element for one grid in this shared semantic space. And here we have another person, the company today element from another person, and here yet from another interview. And we see one thing, that while this is the average, people's single element positions are quite different. For example, person 18 is very close to incompetent company. So he or she perceives the company today as very close to an incompetent company. While this person over here sees that we already fulfilled, almost at least, the company's potential. So quite different perceptions of where we are today. And this is very advantageous, because we can see how people differ. We might see clusters of people. We don't only see the average. But why is this a shared semantic space now? Because the same principle applies. We can project the company's position for this person on the same axis, uncoordinated work by individuals, and we see it has a lower value than for this person. So what applied to the average also applies to the single element positions. That's why it's a shared semantic space. How does this work? Let's go one step back, and we see up here, we see appreciation. So why is appreciation up there? We know from a single biplot we've seen that each axis points into direction. And up here is say, what we see, this shared semantic space, is a superposition of many biplots. So if it's a superposition of many biplots, there must be the axis somewhere of each single biplot. And this is what we see in the next picture. So we see in the shared space, we see that many axes point up here. Well, we see 3 axes, and one end of the axis, or one pole, is feeling appreciated, being treated well, another axis, and yet a third one is appreciation culture. This is person 12, 31, and 9. And what we see here is that this semantic meaning of the axis is very similar. And this is not by chance. This usually happens when we have shared meaning, or let's say elements we construe in a similar way. What happens? Similar axes end up in the same position. So if this is the case, we might say, okay, then it's very hard to look at a space with many axes, so let's aggregate them, let's put them together. And that's what we do here. So this, I might call this pole appreciation, because they're very similar. And instead of having 3 axes now, I use one average axis for the pole appreciation. But you see one thing, when does this make sense? It only makes sense if the axes, the 3 single axes, point in a similar direction. Because if I project from this element on this axis, and on the average axis, it should be about the same. If not, a single axis does not make sense. So we have a prerequisite for an integrated semantic space, which is similar constructs, which means semantically similar, point into a similar direction in the shared space. Then and only then we can speak of a shared semantic space. We will see later on that this is not always the case. So I skipped this slide. What we have now is we have, in this case, I think 4 axes from quality transparency to uncoordinated processes, which in this case are averaged axes. So for a number of axes from single biplots. And this now generates a meaning space. Now we have a shared semantic space where the position of the element and the position of the themes, let's say, or constructs on a higher level, are not have a meaning. The position is not arbitrary, but is based on the single biplots and the superposition of the biplots. So how does this all work? How does this GPA method work? Imagine the following. We have a construct. One pole is utility car, and the other pole is status symbol. Now we have 3 car brands, and I want you to place these brands on the scale below. We have Mercedes, we have Porsche, and we have Nissan. And place it on the scale where you think it fits best. I'll give you a second to do that. Now, the way I placed it on the scale is the following. I placed it like this. Nissan, the rather utility car, Mercedes is rather a status symbol, but not quite as much as Porsche is. I usually find that most people do it like this, and another group of people does it more or less in the same way, but they swap Porsche and Mercedes. Why is that important? Because there's a tendency of us to construe in a similar way, at least in certain fields. There's a principle of homogeneity of perception in sensory research where the application of grid data and generalized procrustes analysis was first used. And they say something, we perceive things in a similar way, but well, that's sensory research. Here we talk about constructions. So we might reframe it or reformulate it and say there might be a tendency of similarity of construction concerning certain things, just as we've seen it now for those three elements when it comes to car brands. And I think that this points to something, to the social side of constructions, where we have shared meanings of elements, where we have shared constructions, which are not arbitrary, but where we are in a social space. And I think this method will only work when we have such kind of shared construction. If we do not have it, the GPA method, which we'll see in a second, will simply not work, and will not yield in general a shared semantic space. So how does it work? Here we have one biplot with two constructs, family car versus fun car, and utility object versus status symbol. We see where Nissan, Mercedes and Porsche are placed, and you can imagine here's a border around it like a sheet of paper. We have another biplot with constructs low quality, high quality, fuel inefficient and fuel efficient, and where the constructs, the elements are placed, where Nissan is high on fuel, is highly fuel efficient, Mercedes is high quality car, and Porsche as well, but not so fuel efficient. And also we might imagine it on a piece of paper, on a sheet of paper. I'll tell you in a second why. So now I said biplots, or the shared space, is generated using superimposition of biplots. So I will superimpose these two sheets of papers. Well, this does probably not make much sense to do it, but that's how we start off from this position. Now, how does the generalized procrustes analysis work now? We have the hypothesis that there is some kind of structure across all elements. The relation of Porsche to Nissan, of Porsche to Mercedes, that is not completely idiosyncratic, but it has a social side of construction, which means that we will find structures which are similar across persons. And the generalized procrustes analysis exploits the similarity in structure. And it says, there's a tendency that Nissan is construed more similar across many persons than, for example, the similar versus Porsche by different persons. So in other words, if we look at all Nissan constructions, they're more similar within each other than if we look at all Porsche constructions, they tend to be similar. If we look at all Mercedes constructions, they tend to be similar, at least in tendency. So the idea is the following. For a second, let's not look at the constructs. We only look at the element configurations. A configuration means the position of one element relative to another. So Porsche to Mercedes to Nissan. And the idea is that this is somewhat similar across persons. So the way GPA works now is that we look at how close is each Nissan to another Nissan, how close is each Mercedes to another Mercedes, how close is each Porsche to another Porsche. And the criterion for us now to find a shared space is that we try to minimize this distance. But as usual, we don't work with distances by itself, but we work with square distances. So these squares is the criterion we are minimizing. We want to get Nissan close to Nissan, Mercedes close to Mercedes, and Porsche close to Porsche. How do we do that? We apply rotation, and we try to move the sheets of paper where the biplots are on in a way that this happens. Now, this is what I will do now. I have this overlay of two biplots, those two sheets of papers. Now we'll rotate them, and you see what happens. Nissan comes closer to Nissan, Porsche comes closer to Porsche, Now again we move away from it, so this rotation of the sheets of paper is not quite the best. Now we're getting closer to the position from where we started, and this is not, they do not match well the element configurations. And now let's see, let's stop at this point and look at the squares between them. We see they are smaller now than before, but are not quite the smallest we can get. Let's move on. So we keep on rotating till we find a position where the squares do not get any smaller. And here we see the squares between Porsche and so on are fairly small. So this is the position we stop at. Now we see that Nissan is close to Nissan, Mercedes close to Mercedes, Porsche is close to Porsche. And we also see the axes, which are rotated along. The whole biplot is rotated, not only the elements. And this is how the position of the constructs in the joint space comes about. Now let's do one thing. Now we have two biplots superimposed. We will take a third one. Let's take this one, which has budget car versus expensive, unreliable versus reliable quality. And again you see Mercedes has reliable quality, Porsche not so much, but it's very expensive, but also high on quality, at least more than Nissan. Let's put it into the generalized procrustes analysis and see what happens. We get this result. Nissan close to Nissan, all Porsches close together, all Mercedes close together. And again we have a new axis here in this space. And we see one thing. We see that unreliable quality and reliable quality, so it's unreliable quality and low quality, are right next to each other. This is not just did not happen by chance, but this usually happens whenever we have shared social constructions of the elements. So this is it's very similar up here. Now let's change something. This is the grid I added, or the biplot I added before, and now I will slightly modify it. I will slightly move the elements. See, I will slightly move them. I will move Nissan to make it slightly more reliable. That's about it. And now let's see what happens to the generalized procrustes analysis solution. This is the solution we had before. This is the solution we have now. They're all close together, as close as possible. But you see that the constructs, the unreliable versus reliable quality construct, has moved a bit. It's not as close to low quality as it was before. So what we see here is that, let's wrap it up. We see that slight perturbations might change the position of the construct. That's not quite what we want. We want actually low quality and unreliable to be as close together as possible in the shared space. We'll see in a minute how we can handle this. So let's wrap it up. We have a shared semantic space that's generated by GPA. The distances between similar constructs serve as a measure of semantic integration, because if the constructs are close together, similar constructs, then there's a real shared space. If not, then there is no real shared space. We also seen that this not necessarily perfect alignment of similar constructs always happens. In the first example, it was the case, but then we saw that small perturbations cause partially at least disintegrated space, where the constructs are not perfectly aligned, although they're similar. So what can we do about it? And this, where the next point starts, I will show you my work on joint procrustes analysis, or generalized joint procrustes analysis. So what is new is this the joint aspect. So what do we join then? The rationale is the following. We want to align constructs which are classified as semantically similar in order to improve the semantic integration of the shared semantic space. How can we do that? First of all, we start with a content analysis. We have a lot of constructs who content analyze, that we do content analysis, and which yields a classification of constructs which are similar in one class. And we incorporate this information from the classification into the generalized procrustes analysis procedure. And this yields a more integrated semantic space, and I call this procedure generalized joint procrustes analysis. So how does this work technically? This is what we started off with. We saw that the criterion we used was to minimize all the distances, the squared distances between the same elements, between Nissan in this case, or here between Paul or she, and between Mercedes. So criterion 1 was minimize square distances between same elements. But we saw that this not necessarily yields a space where constructs which are similar, low quality and unreliable, actually in the same position. So I want an additional criterion. I say, if I want them to be close to each other, then let's incorporate this, and we know that they are similar using the content analysis. Then let's incorporate this as a new criterion. So let's say we also look at the distances between similar constructs. And again, we look at the squared distances. So these should be small. When they are very close together, the axes point in the same direction, they are small. So the second criterion, which is new, is minimize the squared distance between similar constructs to yield a more semantically integrated space. And why I call it joint procrustes analysis? Because we simply join these two criteria. We say they should be valid at the same time. We use both of them for minimization. So we jointly minimize the squared distance between the same elements, standard GPA, and now also between similar constructs, which we deemed as similar using content analysis. We need one more thing. We need a weighting factor, which tells us how much weight we put onto which criterion. So this is between 0 and 1, the weighting factor, and if we apply a weight of 1, all weight is put on the distances between the elements. This means it's standard GPA. If we put all weights on the squared distance between the similar constructs, then it's not at all standard GPA, but we minimize a different thing. And we can choose some value in between. Usually we will want some value in between. So what we see here is now we see a new space with using German political parties as elements. So here we see the party I would vote for, the Green Party, Social Democrats, Christian Democrats, the Liberals, left-wing party, and the party I would not vote for. And this is again the average position of all elements of all interviews, which are 10 in this case, and here the positions for each liberal element in each single biplot, and this is the average from the overlay. This is the result from the GPA. Here we see the constructs on the sides, but not all of them. I will add the rest, but this becomes a pretty crowded space. We cannot see anything. We don't see where the relevant themes are. So what we do now is we apply content analysis to group similar constructs thematically. And one group of constructs which are classified into one group or one theme, I will apply the word or use the word theme from now on. And up here we see that here we see all the themes in this space. So now let's look at just one theme. I will look at theme or class if you want. 17, which contains the following constructs: have environmental competency, well, actually all the same, more or less. And the idea was now to represent it, as we've seen before, those four similar constructs which point into a similar direction, and we found out by content analysis that the meaning is similar. Semantically, we represent it by an averaged constructs. So we get a theme, let's say, a construct theme. So we have environmental competency and have no environmental competency on this side, and the construct runs through here and is the average of those constructs. Now let's look at the whole space. We have themes all over the place. We've categorized the constructs, so these are the themes that come up. I will fade out the constructs completely, and now we get a space that we can understand, where each axis makes sense and is the average of the construct for a single person. So we can apply this now to every single element or the average element, and read it like a biplot we had before. But how well is this representation? How good is it? And this is the new part now. If we look at one theme from all the themes here, and we ask the question, how well are constructs in these themes aligned? We will find that this is very different from theme to theme. Theme 11, for example, which is implementation expertise versus no ability to implement their own ideas, we see that they're very well aligned. All the constructs are very close to the average construct. So this is a good representation of all the constructs. In another theme, theme 6, this is not quite so much the case. Here we have represents a broad mass versus clientelism, and I found out by now that this word does not exist in English. Sorry for the bad translation, but it's Germanism. So here we have 4 constructs, and the average construct is such a good an average or such a good representation of those 4 as in this case, because they scatter much more. Now, can we do better by applying the joint approach to theme 6? That we say, okay, we want to put weights on the distances between those constructs and get them closer together, because this space is not quite correct. Well, we have an integrated space, but GPA does not throw out a perfect space because we see it is not well aligned here. So it's hard to interpret it in just one way. Now, what I do is I raise the weight or lower the weight from 1, which means all weight on the between element distances, and lowered, getting closer to 0, putting more weight on the between construct distances. And let's see what that does. We see it gets lower, we are at 0.2 now, and we see the constructs moving closer together, and we also see the rest of the elements change slightly. Now we end up with a very closely integrated theme 6. The constructs which are supposed to be close together are close together now. This is what we have reached, so we have a more integrated space. Let's do the same to the whole space. Here we have all the constructs, and let's apply the same rationale again. We lower the weight, increasing the weights of the distances between similar constructs to get them closer together. And we see the same happening. The whole space changes bit by bit. And we see groups of constructs gathering here. So now we end up with a space where similar constructs are close together, which looks quite different than before. And this also, of course, changes the position of the single elements, but not so much in this case, because it's a very integrated space in the first place. Now, this is what we get with the weight of 0.05, which does not mean that 95% of the weight is on the constructs, because they cannot be really compared. It's just some value. It cannot be interpreted in terms of percentages, at least with some caution. So now we see the seams in the space, and similar constructs point into almost the same direction. They gather, the gray ones here, gather around the themes. So the wrap up, what have we done? We have seen that GPA and grids are frequently used. I think I skipped the slide in this talk, I'm sorry. But it's the case that this happens only outside the PCP world. PCP does not apply GPA plus grids. The GPA plus grid approach yields a shared semantic space and shows the idiosyncratic constructions to the elements of every person and context. And the generalized joint procrustes analysis improves the integration of the shared semantic space. But there's a missing link to its origin, the grid origin, which comes from PCP. The social side of PCP is not that thoroughly worked out by PCP theorists, which might present a link to the stacking of grids, to the joint procrustes analysis plus grids, but this does not yet exist. Oh, sorry, I mixed up the slide. I'm sorry for this slide slight wrong order here, but we will simply continue here. So what we see is that I did not talk about that before, but is GPA actually used? And we see that RepGrids plus GPA is used in consulting, and software as a service are provided using this approach. Since the 2000s, several German and German-Austrian consulting and software companies have developed, and they make extensive use of multi-grids, that means multiple grids, probably using GPA. They don't say what they do, or only you can infer it, but they do not say so explicitly. And they use large-scale studies. For a single study, up to 1,000 grids. It's huge what they do partially. And these are the companies that do that in Germany. So there are practitioners who are doing that. And if we look at RepGrids plus GPA in journals, we will find that in non-PCP journals, there are approximately 150 papers or more which apply repertoire grid plus GPA. So it's fairly commonly used. If we look at PCP journals, we also find, when we look at how many papers are there, we find, one step before, they have applications in food science, tourism management, health science, so on, so across a wide variety of fields. If we now look at the PCP journals, we find that there are exactly 0 papers using GPA plus RepGrid. Maybe I've missed one, but it seems up to now I have not found one. So the situation is that the grid originated from PCT, but grids plus GPA do not have virtually any link to PCT except a brief mentioning of the origin of grids and its connection to PCT. So there's no connection to multiple grids at this point. Well, there's this famous quote by Don Bannister who said, "Grid method is a Frankenstein's monster which has rushed away on a statistical and experimental rampage of its own, leaving the construct theory neglected, stranded high and dry, far behind." Well, this quote applied to the connection between grid and PCT, but it would even more so apply to multiple grids and generalized procrustes analysis in PCT, where there is no connection at all, at least a worked out one. So this might be some kind of future work. So the link to the PCT. GPA touches aspects of social construction. I've said before that we will only get a semantically integrated space if the constructions tend to be similar, if they're somewhat social. So this will only work if constructions are shared, the social constructions. Theorists have argued that the PCT needs to be linked to social constructive theories. And maybe the GPA plus RepGrid approach offers a method to link these ideas. I'm not sure about that. Ongoing and future work. I'm working on the effect of grid features, for example size, on degree of semantic integration. And it turns out that the number of elements is crucial. The more elements you have, the better the semantic integration of the space. I want to derive rules of thumb to yield integrated spaces. What do you need to do to get an integrated space? And maybe work on the link to PCP theory. Thank you.